Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. And in this video, we're going to be looking at Chapter 2, where we continue to look at using the data tables to find values for properties. We use quality as a way of defining this. In our textbook, quality is a lowercase q, and it's the fraction of mass in a vapor-liquid system that is in the vapor phase. Very important that it's in the vapor phase. So if you do this for any particular instance or property, if Q is vapor, 1 minus Q is therefore liquid, right? And if I do this for any property, and they use M to designate a property, now M might represent the volume, or the specific volume, or the enthalpy, or the internal energy, or the entropy, any number of these variables. But they're going to, for one of our properties that is in the table, I could use any of these with the same definition, all right? And so this is great. It just says the amount that's in the liquid phase times the property value of the saturated liquid plus the amount that's in the vapor phase times the amount of that quantity for the saturated vapor. If you solve this algebraically for Q, we end up with Q is equal to M minus ML over MV minus ML. I prefer to write this, let's write it out, for instance, with the volumes. In that case, I have the specific volume that's the actual value minus the saturated liquid specific volume over the difference between the saturated vapor and saturated liquid volume. If we were to apply that to this particular problem using the numbers from the previous screen, we have 0.03875 minus 0.001229 meters cubed per kilogram, all over 0.059705 minus 0.001229 meters cubed per kilogram. Meters cubed per kilogram over meters cubed per kilogram cancels out. And so I'm left with 0.6416. Okay, so what does that mean? It means this mixture is 64.2% vapor, and the balance, or in this case 35.8%, is liquid. Recall that we had defined the quality for saturated mixtures of liquid and vapor for any property M. So it could be volume, or it could be internal energy, or any of these other properties, as the quantity we measure minus the amount for the saturated liquid divided by the difference between saturated vapor and liquid. So for specific volume, we have it designated here. I'd like us to think through those diagrams, and I call these the rules for identifying the phase, and we'll do it first where temperature is given. So think back for a moment and recall what the diagram for T versus V and P versus T looks like. If you are looking at the graph of T versus V, such as we were using in the previous examples, we have the saturation dome, where we have the big wide saturation region that is enclosed by the saturated liquid and saturated vapor curve. For P versus T, we haven't looked at that one for a couple of videos, but we have for this curve here, which is our saturation curve for liquids and vapors, above at higher pressures is going to be compressed liquid, at lower pressures is superheated vapor, or if we fix a pressure and look across, for higher temperatures is superheated vapor, and for lower temperatures is compressed liquid. So now we have a given temperature. If the other thing I know is pressure, then I'm considering this graph here. If the pressure is exactly on this line, then I know that it is saturated. Okay? It doesn't tell me how much is in the liquid or vapor phase, but I do know that it's saturated, but it's just a point on a line, so I can't give you any additional information. If the pressure is higher, it's a compressed liquid. If it's lower, it's a superheated vapor. If we have temperature plus volume, then I look for the saturated liquid and saturated vapor data. If it's smaller, then it's going to be a compressed liquid. If it's larger, it's a superheated vapor. If it's in between, it's a saturated liquid and vapor mixture, and I can then find Q from that, right? If it happens to be exactly equal to one of the numbers on the table, then that tells me that it is that saturated liquid or saturated vapor. Now, if it's saturated liquid, I know that Q is equal to 0. There is no vapor. If it's saturated vapor, Q is equal to 1. There is no liquid. What if pressure is given? Well, I'm going to play the same mental game. So again, think back to those diagrams. For a fixed pressure, then I would want to come across here, and if it is exactly the number on the thing, then that tells me it's saturated. But it's a point on a line. I can't tell you the quality. If the pressure is higher, it's a compressed liquid. If it's lower, it's going to be a superheated vapor. For volume, again, small volumes are going to be compressed liquid, large superheated vapor, in between saturated. Now let's use this to solve problems again, using the table or these thought processes with that mental image of the diagram as we work these. So, what is the phase and pressure of water at 150 degrees C when the specific volume is 0.2532 cubic meters per kilogram? Now the trick is always begin by going to the saturated table. From the table in our textbook, at 150 degrees C, the liquid volume is 0.001091. Okay, so we're definitely not smaller than that. The vapor volume is 0.392453. Oh, wait, so this is in between, so therefore this is saturated. Now the follow-up question to this is what is the phase, but also what is the pressure? So how do I find the pressure if it's saturated? Exactly, we're just going to use the saturated pressure that we read in the table. So it's next to the temperature. And so in this case, the pressure is 4.7616 bar. Use this. Next, we want to know the quality and specific internal energy of the water at 150 degrees C with the volume of 0.2532 cubic meters per kilogram. Now we have a definition for quality, so we'll apply that. It's going to be the volume minus saturated liquid volume divided by the vapor minus the liquid volume. In this case, 0.2532 minus 0.001091 over 0.392453 minus 0.001091. In that case, it's 0.6442. And the amount that is liquid, if you ever need to know that, is just subtract from 1, so 0.3558. Now the next part is to find the specific internal energy. We know the temperature and we know it's saturated, so therefore I can go back to the tables and look up U for the saturated liquid and U for the saturated vapor. In this case, for the liquid, it's 631.7 kilojoules per kilogram, and for the vapor is 2,559.1 kilojoules per kilogram. How does that help me find the value for U? We're going to use the quality. We know the quality, so now let's write the definition of quality in terms of the variable U. And actually, I'm going to use the other form of the equation. So go back to our definition of quality and use U instead of M, the generic property. It's simply 1 minus Q, the amount that's liquid, the fraction that is liquid, times the U for saturated liquid, plus the quantity that is vapor times the U for saturated vapor. In this case, 0.3558 times 631.7 plus 0.6442 times 2559.1. Now, quality has no units, and the U's both have units of kilojoules per kilogram, so this will have units of kilojoules per kilogram. My value for U at this condition is 1873.3 kilojoules per kilogram. We've now looked at using V and U on these tables, but we still have H and S to go. I'll save S for a later day, but let's look at enthalpy, or H, next. So enthalpy is simply another energy state property. It is really just a combination of internal energy and the product of pressure times volume. We're going to make sense of this pretty soon when we start talking about the first law of thermodynamics. But for now, just simply this is a definition. So H is U plus PV, and I can do this as either the extensive version, the specific enthalpy with specific internal energy and specific volume, or the molar enthalpy with molar internal energy and molar volume. Let's do another example problem. We want to do temperature and enthalpy of water at 1 bar with specific volume of 2.406 meters cubed per kilogram. So we're going to again go to the saturated steam tables and look up this pressure and that data. Pause the video. At 1 bar, the saturated liquid specific volume is 0.001043 meters cubed per kilogram, and the specific volume of the saturated vapor is 1.6939 meters cubed per kilogram, so this is larger than both of those. So therefore, we know that this is superheated. Now, if it's superheated and I want to know anything at all about it, then I next need to go to the superheated tables. So flip to the superheated tables and find 1 bar in the superheated table. When you look this one up, scroll through the table until you find 2.406 meters cubed per kilogram, and you'll find that this is an entry in the table. Great. The temperature associated with that entry is 250 degrees centigrade, and the specific enthalpy associated with that one is 2974.5 kilojoules per kilogram. Next, we're going to look at a problem where it isn't directly in the tables. So this time, we're just going to change the volume to 2.22 meters cubed per kilogram. Just a moment ago, we looked up and found that at 1 bar, the saturated liquid and saturated vapor volume are both smaller than this, so this is still superheated. But when we go to the superheated table, this number is not in the data table. The numbers that we see in the data table are at 200 degrees C and 250 degrees C, where the volume is 2.172 and 2.5 2.406. So how are we going to determine exactly what the temperature is? Is it good enough to just say, it's somewhere between 200 and 250? Or is it exactly halfway between? What we want to do is we want to basically fit a straight line to these 2 points. So if I have the temperature and the volume, so at 200 it's 2.172, at 250 it's 2.406. If I considered a straight line between these, I'm trying to find the point where the value is what I have given so that I can estimate the temperature. Now, if you know how to do this in Excel using the forecast function, I highly recommend that you learn how to do that. It will save you a lot of pain later on, but we're just going to be fitting a straight line to this. This is called interpolation. So if I interpolate, what I'm doing is I'm saying that the slope between the point I want to know about and one of these, okay, say that one, is the same as the slope of the entire line. So in this particular case, t and 2.22 are the two values. I know 2.22, and I'm wanting to know what is t. The slope between these 2 points is t minus 200 over 2.22 minus 2.172. And the slope of the full line is 250 minus 200 over 2.406 minus 2.172. And I can solve this for t equals 210.3 degrees C. Now, I haven't pointed this out yet, but you'll notice that the table is basically with 4 or 5 significant figures. So I try to always use numbers with at least 4 significant figures when I do answers here, okay? Any less than that is going to cause precision difficulties when I go to more advanced topics, okay? All right, so however you chose to do this fit to a straight line, T is 210.3 degrees C. So what about H? They ask us to find the enthalpy. Well, same thing. I could also do H versus V, right? In that case, H minus 2875.5 over 2.22 minus 2.172 is equal to 2974.5 minus 2875.5 all over 2.406 minus 2.172. And therefore, I find that the enthalpy is 2895.8 kilojoules per kilogram. In this final example, we want to calculate the internal energy of water at 1 bar when the volume is 2.22 cubic meters per kilogram. But I want to do the calculation 2 ways. Really, I'm doing it 2 ways just to make the point that the definition of H equal to U plus PV is correct. But let's do it first by, well, we just figured out what H and volume were, so let's use that to calculate U. So U is equal to H minus PV. In this case, 2895.8 kilojoules per kilogram minus 1 bar times 2.22 meters cubed per kilogram. Now, the units are sort of garbage at this point, so we need to do a unit conversion. You can do this a lot of different ways, but I am going to teach you one of my favorite tricks, and that is that in this course, you're going to find that R values, those ideal gas constants, if you have a list of those with different units, they can be incredibly helpful. So in this case, R is equal to 8.314 kilojoules per kilomole Kelvin, but there's also another version of it that has bar in it. R is also equal to 0.08314 bar cubic meters per kilomole Kelvin. And two things that are equal to each other can be used as a conversion factor. In this case, 8.314 kilojoules per kilomole Kelvin divided by 0.08314 bar cubic meter per kilomole Kelvin is equal to 1, right? They're equal to each other. The kilomoles and kelvins cancel with each other. The bars and the cubic meters cancel with this, leaving me with units of kilojoules. And so now then I can 2895.8 minus 222 kilojoules per kilogram. And so U, and this should have a little circumflex on it, is 2673.8 kilojoules per kilogram. All right. Now, what if we did the second method, interpolate from the table? Well, I'll go back and look up all the values, but U minus 2658.2 over 2.22 minus 2.172 is equal to 33.9 minus 2658.2 divided by 2.406 minus 2.172. Using this method, U is equal to 2673.7 kilojoules per kilogram. Now, the last digit is different, but from the tables we expect that we can get to 4 significant figures always, and we should use those. The 5th digit is in doubt, and that is where we see a difference. Now that concludes this video lesson. When we come back, we're going to continue looking at Chapter 2, but we're going to look at other things we can do with these properties. Thank you very much for your time.